delayed for 5 hour Sunday, so I couldn't come here in time. Today we'll start our first lecture in condensed matter physics. And I thought we'll get something light for the first day. I will try to discuss what is condensed matter physics. But I will try to discuss this question or this issue using a very kind of unusual approach. Basically, I will try to tell a story of light. And through this story, we'll try to bring out some issues and concerns and what people worry about in condensed matter physics. And the story I'm going to tell actually is a story probably many of you already know about. But here, I try to emphasize on the experimental aspect of light, how we understand light from all kinds of experiments, how the experiments force upon us a theory of light. So, in some sense, scientists are like a detective, they try to understand all kinds of mysteries. Okay. So here, the mystery is light, we know the lights. And we thought we know the lights. So the question is, what is the question? Okay. And to start any exploration, we usually ask a question, and the last right question is very important, such as, what is light? And so this is a very simple question. So therefore, it has a very simple answer. Light is something coming from the sun. But certainly, this is not what we mean. Okay. What you really want to understand is what is this thing coming from the sun? What is light itself, not where it's come from? Okay. So historically, there's two theories. One theory is a particle theory. It's a light in the light beam. It's just like light. It's just a beam particle because this beam can be blocked, say, partially. It's like a beam particle which can be blocked partially. So this is a very popular theory of light. And there is a not so popular light. At first looks very strange. They think a ray of light is a wave. It's a wave theory of light. I can imagine like 100 or 200 years ago, looks like this wave theory looks like just an unnecessary complication. The particle theory seems so natural. Have a vacuum which is empty. You have something in the vacuum, then the beam particle corresponds to beam of light. It seems very natural. But anyway, like any theory, when you have two competing theories to explain same phenomena, so there's issue which theory is correct. Okay, so then it depends on which theory can explain the experiments. So that became very important. So the simplest experiment phenomena for the light, the most common one would be the refraction. When the light beam going through a material is a band, it's kind of band in the direction which is towards this normal direction of the surface. Okay, or it's band inwards. So according to particle theory and wave theory, this refraction have a different interpretation. One interpretation according to particle theory is that when the particle beam enter the material, it feel the force which kind of draw into the material, pull into the material. So the beam is bent in its normal direction. And when the exit material, they feel the opposite force of the beam is bent backwards. Okay. And for the wave theory, it have another picture. You know, when the wave front hits the surface, the wave propagates different velocity in the material. So the wave front gets bended. Okay. So in some sense, both theory, both particle theory and the wave theory, explain the refraction very easily. Yes.
But don't we know that when the light refracts, it goes slower in the medium? So
Yeah, so this is a question. So, but although both particle theory and wave theory explain the refraction, it have a different prediction. That's exactly what you said. The particle theory predict that light will go faster in the medium, and the wave theory predict light go slower in the medium. Okay, now we have something experiments. So this is the key actually. That's one message. You know, it's usual to have two theory for same phenomena, and then if both theory can give some prediction, and if prediction are different, they just test it. And example, and I just said, if you do the experiments, we test that, the wave theory wins because indeed the measured velocity of light inside the material is slower, not faster. So this is quite a lesson because the wave theory seems so strange, you know. The particle theory seems so natural, but it wins. It reflects truth. But certainly, refraction is a simple phenomenon. But the most definitive experiment for the wave theory is the interference, because the wave theory have a particular property that two waves add up, you may get something smaller. You know, if two waves add in phase, you get something stronger. But if two waves add out phase, you get nothing. So not like a particle beam theory. Particle theory, two light add up, always enhance. But the wave theory is different. So therefore, this certainly this interference in this Newton's ring, this two glass with a gap which is varying distance, and the wave reflect from the upper surface and lower surface can add or cancel. You know, you get these rings. Okay. If you do this, certainly, if you do this experiment for light with different colors, we find the ring at a different position, which essentially reflect the wavelengths of light. So this gives us this the correspondence of how the wavelengths and the color is connected. So all experiments. You know, so it's not something. The thing here, I emphasize that this is not something. This is not a statement in the book. There are really actual experiments there. You really do the experiments. You do see this. Yeah, this the way you can measure the wavelengths, so the different colors. So here comes an implication. If wave theory is correct, it means something. Okay. So what that means? Because you can see the particle theory at the beginning is very natural because we think the vacuum is empty. Then the things are, you know, the light or other things are just something placed in the vacuum. Okay. But if vacuum is empty, you know, to have a light wave travel in some empty thing, it's hard to imagine. So there's a consideration that maybe the light is a wave means the vacuum is not an empty thing. It's actually a dynamical media, and that seems more natural. That is so the assumption that the vacuum is really empty really is what led us to think light is a beam particle. If light is a wave, it probably means the vacuum is not empty. So maybe it's more proper to view vacuum as like an ocean, you know, with the water in it. And then the waving of water, like a sound wave, like a sonar passing between submarine, actually can be viewed as a light wave in the universe, which you can view as an ocean. And then the bubble maybe like a material. And a matter can be a bubble in the ocean. So therefore, the wave theory seems to suggest that the vacuum is a dynamical medium. Okay. However, things are not that simple. Okay. And because light as a wave is a very special kind of wave, as reflected by this phenomena, I think it's called the birefringence. So there's some crystal, and you have this double image. Okay. So basically, this phenomenon is because since the light beam can have two different refraction for certain crystal. So different refraction and light will bend differently. So somehow you can get the two double image. Okay. And this phenomena suggests that, so in the particle theory, to explain this, you can say maybe light wave is it have two kind of particle, particle A, particle B. So particle A and B feel different force, so they have different refraction. Okay. Well, for the wave theory, this double image property is attributed to a polarization for light. So they think the light actually is not, it's not just any wave, it's a special kind of wave, where it have two kind of vibration direction or polarization direction. Like if light propagates in the horizontal direction, one polarization direction is a vertical, another is horizontal perpendicular to the board. And so therefore, the light wave have these two different modes. And the two different modes, if a crystal have a low symmetry, may have a different velocity in a crystal, and then they bend differently. So we have this phenomenon. Okay. So so this polarization probably give us a lot of headache. Basically, it says that we can no longer regard vacuum as a liquid. Because in the liquid, we do have a wave, but we cannot have a wave with two polarization. The reason is following. You know, in the liquid, we have a liquid is formed by particles which have a random distributions. Okay. And so then we can see for such kind of media, what kind of wave such media can support. Well, we can try to compress. We can compress it, and the compression means it's compressed, decompressed. So this density can move around. Okay, so this is density wave. So some region have a higher density particle, some other region have a lower density, and they kind of propagate. So we have a density wave. Okay. But density wave is kind of longitudinal. It's a vibration direction. It's perpendicular to the propagation direction. And we only have one such mode because there are only one propagation direction. We don't have two density modes. Density mode is just one mode. So we have trouble to explain the two different polarization. Let me try to see, can we have a transverse polarization? Okay. For the liquid, we couldn't. Because a transverse polarization comes from the shear deformation. That's a key. And the liquid already have kind of random distribution. If you do a shear deformation for liquid or shear deformation for random distribution, you still have random distribution. Nothing changes. So unlike compression, when you compress or decompress, the density changes. When you do the shear deformation, nothing changes. So in the liquid, shear deformation actually, here I'm actually doing shear deformation. You can only see that in the boundary, but in the middle, you couldn't see anything. So shear deformation is do nothing operation for the liquid. So therefore, so the liquid cannot support any shear deformation. So it cannot support the transverse mode. So it only have a one longitudinal mode. Okay, so that essentially says that we cannot view our vacuum as ocean because if you do so, the wave in the ocean or in liquid only have one mode, but the light have two mode, two transverse mode, and this is only one longitudinal mode, so it doesn't work. Yes?
So the surface wave, can that be transverse?
Yeah, surface wave can be transverse, yeah. But yeah, maybe if the universe has a boundary.
Right, that's what I'm saying. Like, are we a boundary of some other universe?
Yeah.
And
That's very interesting. That one is not, that's we regard as a longitudinal.
right.
Because if you are the boundary of the universe, always transverse, but in the
3 dimensions.
yeah, in the direction normal to our three-dimensional space, well, that's still scalar, not the. This is actually this comes to the very interesting issue. So that's this question related one thing. Okay, so let's come to this. Here I hide something actually. I skip over something. So let's just say the light has two different modes. This double refraction means it has two different modes. But how do you know it's two transverse modes? Okay. So maybe the vacuum ocean is like two fluid, you know. One fluid is like oxygen, another fluid like hydrogen, and you have a density mode of hydrogen or density mode of oxygen. So then you have two modes. Okay. Then the two modes, so maybe there's two modes in the light wave because our ocean have two components, have two density modes. Okay. So this is again experimental question. So I ask the students to think about these design experiments. How do you rule out that the light wave is not two density mode, but actually two transverse mode? So this again experimental question. Again, we have two theories. One theory to say that yeah, you know, they say the light has two modes, but how do you know? So there are two opinions. One opinion is the both modes are longitudinal, just like two different density modes. We have two components. Another opinion is that we have two transverse modes. That's very natural. In 3D spatial dimension, we happen to have two transverse modes. So which experiments tell us actually the two transverse mode is a better theory, not the two longitudinal mode is better theory? So again, so here that's what I try to emphasize here. Although there's a lot of theory, a lot of equation, but I try to emphasize all these equations just reflect those experiments. And we try to, a lot of physical issue is really try to be answered by experiments. Can we think about the experiments? That's one thing. So if a liquid doesn't work, maybe our vacuum is a solid, you know. In a solid, indeed, we can have a transverse mode. Because in a solid, it's a form a regular array. So the shear deformation is no longer do nothing deformation. Shear deformation indeed change the liquid, change the solid configuration. So the solid can indeed support two transverse modes. Okay. But there's one problem. The solid also support a longitudinal mode. Okay. So if our vacuum is a solid, then the light wave should have a 3 mode rather than 2 mode. Okay. Both transverse and longitudinal. So here's what we are facing. We know light wave have 2 transverse mode. But the liquid only support a 1 longitudinal mode, so therefore the vacuum cannot be a liquid. A solid support 1 longitudinal mode and 2 transverse mode, also disagree with what you see in the light. So the vacuum cannot be a solid. So we still don't know. If we think light is a wave, we think the vacuum is dynamic medium. At least we guess the vacuum maybe is dynamic medium. But for a long time, we just don't know. And so we don't know any example of media which support a wave with only 2 transverse modes. So this is a physical difficulty. And after so many failures, and we start to wonder, maybe vacuum is indeed empty. this ether picture of ether is not right. Okay, but still, this is the problem. However, despite we don't know what is waving, for some mysterious reason, we managed to obtain a theory for light wave. And so, when I think about it, it's a little bit strange, Usually, if you know what is waving, you get a theory for not wave. But for some reason, even though we don't know what is waving, and we get a theory for light wave, even though without knowing what is waving. So our theory starts from the magnetism. That is, we know magnetism a long time ago, like 2,000 years ago. Magnetism. Oh, this is the first compass. So this is not a spoon. This is a magnet. It's placed on a very smooth surface, so it's pointing to the.
From where was this from?
I don't know. It's maybe around 2,000 years ago, I think. Okay. So we know the magnetism is just some material have a magnetic property. It can interact with another material with a magnetic property. Let's see. Over a distance without contact. Okay. And here's something, I will emphasize something on the experiments. Now here I try to emphasizing the importance of philosophy. So certainly the 2 things interact without contact seems very strange. And but certainly not strange. If experimentally they interact without contact, no, not like that. So then you just accept that's experiment. So you should accept that. But this is a situation where someone who have a principle, let's say, nothing can interact without contact. This should be a principle. Okay, this principle led to the concept of magnetic field. You say that the magnets two magnets don't interact without contact. Actually, so one magnet create something we call magnetic field. Then this magnetic field contact with other magnets, and then that's how interaction happens. Okay. Certainly, the concept of field is not new. A lot of magical person have fields. Okay. And we also have electricity. Electricity is things have a similar behavior as magnets. They also can interact over a distance without contact. Certainly, if you are the person who at this time ignore the experiments and insist on the principles, then one can say that yes, the electricity also have an electric field, as you can see with the help of the hairs of this person. That's how we visualize the electric field. Okay. So at the beginning, the electric field and the magnetic field, or electricity and magnetism, seems as 2 independent phenomena. But however, later we find that related. The current passing through the wire can generate a magnetic field, which is changing the direction of this magnetic needle. And if you move the magnet through the coil, it generates electric field and drive the current through the coil. So you can see that. Okay. So these two phenomena really says that, again, both are experiments. Really say that electricity and magnet are related, and Maxwell kind of summarized all those phenomena in his famous Maxwell equation. Okay. So, so from this Maxwell equation and or from this mutual induction, that the changing electric field generates magnetic field, and the changing magnetic field generates electric field, and etc. We can find that electric field and magnetic field can propagate in a vacuum and sustain itself, and it became a wave. You know. It's very impressive. You know, at the beginning, you just have two magnets interact over distance. And when I first learned Coulomb's law, you know, we have two charged particles with some force. The electric field was introduced just simply for convenience. You know, it's some vector proportional force just for convenience. But this mutual inductance really gave electric field and the magnetic field its life. So they are really just like matter itself, can sustain itself and can propagate. So this is a story where this principle win over the experiments. So the field do exist. And using from the experiments of mutual induction, Maxwell find this electric wave and the light wave have a similar velocity. Actually, at the beginning, I think the velocity differ by about 20 or 30%. You know, but they are both very, very fast. I think Maxwell don't believe you have two kinds of wave which can travel so fast and be different. So even despite there's some error, they still think the electric wave is a light wave. And later, the more accurate experiments really show that indeed it's true. So basically, they try to show that so Maxwell's theory really is one of a very successful unification. It's a light, magnetism, and the electricity are really the different side of same coin. Yeah, that's a one of very important unification. And so certainly, this electromagnetic theory also explains the two polarization. And the light wave can travel in the horizontal direction, but the electric field vibrate in the vertical direction, so it's transverse mode. Okay. So, but however, despite we have such a detailed mathematical theory for the light wave, we still didn't answer our first question. What is a waving? Basically, we do have two amplitudes, electric field and the magnetic field. But we don't know their amplitude of what operation, vibration. You know, I still remember when I first learned Maxwell equation, that's something which came to mind first. I mean, there's a wave, there's some amplitude of vibration, amplitude of wave, but what is a waving here? And then after reading many, many books, and after teacher repeatedly tell us the Maxwell equation, Maxwell equation, Maxwell equation, then can forget this, the original question, don't ask. just E and B, don't ask what is waving. Okay. But however, I think one should insist on asking this question, what is waving? Okay. We already see that the liquid and the solid doesn't work. But however, here I want to emphasize one point. The liquid and the solid really support a very different kind of wave and with very different kind of wave equation. Okay. In the liquid, the wave equation is just an ordinary wave equation. It's like Euler equation. So there's a density, and we have this two-time derivative, and it's a velocity, and a spatial derivative. So that is That's the wave equation for the liquid. For the solid, the wave equation is more complicated. I think something like that. It's actually a vector wave. Okay. Then here we could have a tensor I, J, U, K, and we could have a tensor. Let me call this a J. No, I already used J. I, J, K, L. Let's use L here. So L, I, J, K. I kind of lose on the upper and the lower index. Okay. So this may be called the Navier's equation. And but here, what I want to emphasize is that the organization of a particle in the liquid and the solid is very different. In the liquid, we have a random organization. In the solid, the particles form a regular array. So this is the concept of order. We know that the liquid and the solid belong to two different phases because they have different order. And then what I try to emphasize here is that the different order actually led to different wave equation. So this is really a principle for emergence, actually. So different phases have a different order, and different order led to different property. So what form those particles is not important. Whether those particles is hydrogen, or oxygen, or whatever, it's not very important. It is their organization is more important here. Whether they have random distribution, if you have random distribution, it always gets to the Euler equation. If you have this regular array, it always gives you a Navier's equation. So it's really the order led to the wave equation. Then with this, when we ask this question, and then we can ask following. So the right question to ask is that how should the particle organize so that the wave would have only two transverse nodes? And another way to say that the wave equation happens to be Maxwell equation. You know, different organization give you different wave equation. Can we find the organization which gave us Maxwell equation? Maxwell equation. And actually, such organization does exist. So this is a picture of the organization which can give us the wave with only two transverse nodes. So in this case, the order is following. First, we have a particle. Particle first form strings. Okay, so like polymers. Okay, and then string fill the space. So actually, this picture can be viewed as a picture of a plastic. So in the plastic, we have a lot of polymers, and the polymer kind of entangle, have random distribution. In the plastic, polymer just have random distribution. Okay, so then I ask, you know, when you have a plastic, and the plastic also have a wave in it, whether the wave in the plastic is described by Maxwell equation or not. The answer is no, because the plastic is fixed. The string, although random, but only one configuration is realized. However, you can imagine the situation that in the plastic, the two string can have very strong quantum tunnel. You know, two string like this can tunnel into this direction. So if quantum tunneling between two strings is very easy, then the plastic may so-called quantum melt. So therefore, the ground state of the plastic is a superposition of many, many different string configuration, different random string configuration, not just one string configuration. In the plastic, all those strings random, but only one configuration in each plastic is realized. So this is different from so-called string liquid. The string liquid is a state where the string have random configuration, but have many, many random configuration. What do you mean by many, many? Means the ground state as a quantum state is a superposition of many, many string configuration. this is very much like in a liquid. So here, when I say liquid, I really mean the superfluid or boson condensed, particle condensed states. So it's not just, if only one random configuration realized, we don't have liquid, we get the glass. In the glass, the particle have random configuration, but only one is realized. But in the liquid, we have many, many random configuration. What I mean is that the ground state of this quantum liquid is a superposition of many, many random configuration. And this have a jargon called condensed, called particle condensed. Means superposition of many, many different configuration. So therefore, the string liquid is very much like that. It's not like a glass. It's not like a plastic. It's like a glass. It have only one configuration. But we have if the quantum fluctuation is very strong, the ground state is superposition of all random configuration, then we get this string liquid states. Okay. So then the next question is, what is the wave in this string liquid? Okay. And certainly the question that's whether the wave in the string liquid have only two transverse direct polarization. That's a question. So how do we think about this problem? Well, we can think of this problem just like we think, just like in this case, in the liquid case. So what is a wave in a liquid? Well, it's just a density of a particle. The density can fluctuate and propagate. This propagation of a density fluctuation is a wave in the liquid, in the particle condensed phase. In a string condensed phase, or in a string liquid, we can just follow the same line of thinking. It's just the density of strings. In some region have a more string, other region have a less string. The densest string give us a wave. Okay. And but the interesting is that the densest string is a vector. It's not a scalar. Because string have a direction. When you say a region have a more string, you say more string in which direction. So unlike a density fluctuation in the particle liquid, there's a scalar, just one number. But density in the string is actually a vector. And also, here I want to add another condition. The string we consider here have no ends. They form loops. If a string only form loops, have no ends, then this density have a very special property. It have a zero divergence. Because what it really means that if you're using a vector to describe a density of strings, and the string is a loop, have no ends, then divergence of such density should be zero. One way to think is that we can view this string as a flux line. You know, string always form a loop means this flux is conserved. If a flux conserved, then it cannot have any divergence. Okay, the flux cannot just produce from nowhere, so have zero divergence. And the way with zero divergence will be transverse. Yes.
Can we think of this in a classical analogy where top string has only two translational transverse lines? I'm not sure.
No, what I really try to say is the following. So you can see, suppose we have let's imagine we have a string all pointing in one direction. So that means the string density is a vector pointing in that direction.
Right.
Then the trouble is that then we try to change the string density along that direction. We have trouble. Because string all in that direction, it cannot be changed because the only way to change the string in that direction is to make some string ends disappear. If string cannot disappear, if string cannot have end, then it cannot change along the direction of string. It can only change perpendicular to string, just like what you plot here. So this is the property of the wave of the vector field which are divergent. So therefore, it's only have a transverse mode, no longitudinal mode. This is the key. Yes.
From the graphic, the animation there, could you just explain again how the density is a vector?
Okay. Yeah. Unfortunately, that's one important detail I didn't plot here. The strings are oriented. Strings have orientation. If strings don't have orientation, the storytelling is wrong. But it's very hard to put an arrow in all these lines. Yeah. So string need to have orientation, and so therefore in this region, you have a more string in one particular direction. It's have orientation. It's oriented strings. Unoriented string also give you something, but not lightweight, but some other interesting things. Okay, that's it. So it turns out that the light wave can be viewed. Maybe let me say that the wave in the string actually satisfies the Maxwell equation period in the string liquid. It's basically a wave described by this vector density of the strings, and such a vector density was commonly known as electric field. Actually, electric field is this vector density of strings. And the equation satisfied the electric field happen to be this equation of this wave inside. Yes?
In this picture, where does the magnetic field arise?
You don't see magnetic field. Magnetic field is canonical conjugate of electric field. So it's described the velocity of electric field, means the change of the electric field. So that's how to write. So you directly see the electric field, but magnetic field is a canonical conjugate. It's like momentum of the electric field. If you think electric field as a coordinate, the magnetic field like a momentum. Yeah. Okay. So basically that's it. So if you have a quantum liquid of oriented strings, then the wave in such a quantum liquid is a Maxwell equation, satisfied Maxwell equation. Actually, this will be a topic of this class. And so in this class, we'll first do the superfluid, like a wave, that's particle condensed states, and study their waves. Then later, we'll study the wave in the string liquid and try to show that indeed Maxwell, this is indeed the Maxwell equation. This is just some pictures. Okay. So it is possible that maybe the vacuum is a string liquid. It's not a superfluid where you don't have a longitudinal mode. It's not a solid which have a longitudinal mode and a transverse mode. If you have a string liquid, then it's only two transverse mode, no longitudinal mode. So what is the charge? Okay. Since we know that the electromagnetic theory for light, the charge is involved. But the charge now became very simple. It's end of string. Because the charge is source of electric field, or source of a string density. So if string only form loops, so the string density cannot appear or disappear. But if string have end, then that means the electric field can be generated from, originate from some place. Okay. So this is a picture that's a plus or minus charge. So connect by, I think there's a 25 string here. So you can connect them. And so those are a picture of a dipole with a string connecting them. So end of string is electric charge. Actually, it interacts with the fluctuation of string, just like charge interact with electric field. We know that the charge interact with electric field. So the end of string indeed interact with the fluctuation string density, just like charge interact with electric field. Okay. And So the dipole radiation, this is dipole radiation. You know, when the pulled end of string around the string may close from itself and radiate backward of itself. So this is dipolar radiation. Okay, so actually this is a picture that's light. So this part is light, and end string is an electron. So this is a picture of unification for electron and the lights. Okay. Yes.
What is the magnetic monopole in such a picture?
Yes. Maybe let me say another point, then I answer your question. Here in this picture, unfortunately, only reflect one thing, is that I only reflect this the electron carry charge, you know. So electron behave like end strings carry charge. But one thing I didn't emphasize, I may not be able to, I don't know whether I can cover this kind of, that is, electron also can have Fermi statistics. So the particles which form the string are all bosons. Even though the particles form the string are all bosons, the end string can be fermion. So it's depend on what kind of wave function you're talking about. You know, I mentioned that the string liquid is a superposition of all kind of string configuration. If a superposition all have the same phase, means if all string configuration have the same amplitude like 1, that's the simplest string liquid. In that case, the end string is boson. But however, we can modify this amplitude. Like if two string for this kind of string configuration, the superposition is have an amplitude have a plus sign. If two string get a link, have a minus sign. If this amplitude can change sign, you get different string liquid, different string condensation. And for different string condensation, the statistics of end string can change from boson to fermion. So actually, I literally means that the end of string can really unify the electron and the lights, including the Fermi statistics of electron. For the monopole, there are also multiple. I'm going to discuss this maybe in a class. That is, you know, string liquid is a particular ordered phase. Any ordered phase always have a defect of order, which appear as excitation. The end of string is one type of defect. So that's the electron. It's one type of defect. Because the string liquid always is formed by the loop of string, no loose end. So that's no defect. If some string have open end, then that's one type of defect, that is the electron. But string liquid have another defect, which corresponds to monopole. That is, let's consider string liquid where the all different random configuration string all have a phase amplitude of 1, for example. We can modify this amplitude in such a way that we pick a point when the single string wrapped around this point is a phase changing from 0 to 2 pi. Okay, and such defect. This also represents defect, but in the wave function, not in the string itself, but the wave function amplitude is modified, and such this corresponds monopole. So our conclusion is that this string liquid picture always have monopoles. It's unavoidable. There's always a monopole. It's just like so actually the monopole in the string liquid is more like the vortex in the superfluid. That's due to the change of wave function. In the vortex, it don't have correspondence of end string. So only have one type of defect is a vortex. In the string liquid, have two types of defect. Monopole like a vortex, and end string is a new one, which have no analog in the superfluid. Yes.
That means the light is the collective motion of a string.
Yes.
And the motion of a string just the lowest order vibration of a string. That
Yes.
means if we have the higher order vibration, that we can get more complex field.
Okay, let me answer in that. Okay. So this is a two vibrational solid. Let's give a sound wave. So I say the sound wave in the solid is a vibration of atoms in the solid. So I say that in the same Same way, like the collective motion of string give us light wave, just like the collective motion of an atom in the solid give us sound wave. Okay. And regarding the more complex vibration is about falling. In a solid, when you have I'm talking here is a long wavelength limit of sound wave. So the dispersion relation is linear. When the sound wave have a short wavelength, the dispersion relation became like sine. It's deviate from linear. You have Brownian zone and all things like that. So indeed, the similar thing is true for this wave string. That is maybe. Yeah. So maybe this is long wavelength picture. In short wavelength picture, who knows what's going to happen? So in the long wavelength picture, in long wavelength limit, you'll recover the Maxwell equation. But in short wavelength limit, it can be anything. Just like the two equations I write down there, like the second equation describes a sound wave in a solid, but only in long wavelength limit. Yeah.
So this is not relativistic?
No. But in the long wavelength limit, it's approximately relativistic. But at short wavelength limit, we don't know what's going to happen. It depends on theory. Okay. So here maybe the point is that this three picture means three possible baby universe. I think probably you have heard this multiverse baby universe. So maybe one of them is this. In this baby universe, we don't have this Bell-Freitas. We don't have a double refraction. In this one, we can have a triple refraction. We have three images. We have a crystal which gives us three images. But here is where we live. But the point is that actually I'm not talking about energy physics here. I'm talking kind of semantic. So what I'm really trying to say is that we don't know. It's hard to say whether all the vacuum is a string equal. Maybe that's not quite the point. But however, it's very interesting to see in a real world material, we see this order and this order. So it's quite interesting to see, can we find this order? So this really connects matter research. That is, can we find a new state of matter, a new kind of order? And you may say this order is very hard to find because in a plastic, the tunneling barrier between two polymers is very high. It's hard to see they can tunnel through each other. But here I want to emphasize the string don't have to be formed by atoms. They can be formed by quantum speeds. For example, in some magnetic material, we can view the state where we spin O down as reference, as no string states. And loop of up spin is our string. Okay. So therefore, you can view this picture as this background just O down spin. This red line gets a loop of up spins. It's a particular magnetic states, quantum magnetic states. And in that case, we probably some kind of spectral magnetic material can realize this. And then the spin fluctuation in those materials, like a spin wave. So that would be such a Maxwell equation. Particular spin wave, such a Maxwell equation. That's quite interesting. Okay. So to summarize, that's although we're talking about the space, the light, the electrons, elementary particle or matter, things like that. But here the point of view is that the space is just a material. It's a particular kind of material, and so it have all these elementary particle are just a defect in the order in this material. Okay. So this is kind of an issue. So that's what I'm trying to say. I'm using this light as an example to demonstrate some kind of a way of thinking in condensed matter physics. Is that we have underlying degree freedoms. The underlying degree freedom actually is more correctly called qubits, means like a spin. in the material. Spin up, spin down is qubits. Okay, that's underlying. And so the qubits may have different orders. If the qubits have the string orders, then we have a Maxwell equation and the electron. So just particular. So this way of viewing light is really trying to view space as a particular material. So now we can answer what is condensed matter physics at the end. So condensed matter physics actually there's a lot of answer to that, but here in my class I try to emphasize one aspect. The condensed matter physics study the organization of particles or qubits. So it's a study the order, all different order. So here we describe three order. It's a liquid order, or more precisely, the superfluid order, the crystal order, and some kind of string liquid order. Okay. And then the property of those material or this order are mainly determined by this organization. You know, like for example, we know that the liquid have don't have a shape and solid have a shape because they have different order. The liquid have a random distribution and solid have a regular distribution. And the random distribution cannot resist shear deformation because shear deformation is a do-nothing deformation for that kind of order. So that's why the liquid cannot have a shape. And the solid can have a shape because the regular lattice order can resist shear deformation. So you can see this mechanical property, or density wave, sound wave, all kind of property, they can all emerge from some kind of orders. Yeah. It's for the long time, we thought the density wave, spin wave, and things like that can emerge from orders. But only recently we realized that the even Maxwell equation and Dirac equation can also emerge from some order, like a string order. So in some sense, the different order gave us this condensed matter physics. Now, if we go beyond condensed matter physics, now this quantum counter gave us everything. And certainly, one of our current research is that to fill in here, Einstein equation. Can Einstein equation emerge from some kind of order? Just like a Maxwell equation emerge from the wave in the string liquid. What are some maybe membrane liquid? Actually, people tried membrane liquid, didn't work. The membrane liquid gave us a special kind of gauge theory. It's a gauge theory with a rank 2 antisymmetric tensor field. And that's correspond to the membrane liquid. And unfortunately, Einstein equation is rank 2 symmetric field. So rank 2 antisymmetric field is a membrane. It's a membrane liquid gave us rank 2 antisymmetric tensor field. And that's also a generalization of gauge theory. From vector potential to rank 2 antisymmetric tensor, we can get that. But we don't know. Yeah. So those are the questions. And so in this class, I will mainly using the classical, semi-classical picture, try to understand this connection from an organization or order to its dynamic property, like waves and thermodynamic property and things like that. Okay, yes. So any questions? Okay, and